Now let's take a look at some real circuit examples for our current amplifier configuration. We're not going to spend as much time as we did for our current amplifier or our shunt series as we did for our voltage amplifier, but I still want to take a brief look at one op-amp circuit and one discrete device circuit. So let's start with this op-amp circuit here. So one thing to notice is, of course, we have a current amplifier. So we have some input current on the left. And because we're saying it's not ideal, at least in this first drawing, we're going to amend this in a little bit, we've included some source resistance R sub S. On the output side, we see our output is also a current, I out. Even though we do also have a output voltage label, what we're focusing on is our output current coming out of the op-amp. So again, how you define your outputs and inputs can be important in terms of what type of circuit analysis you're doing. We have labeled some blue currents as well, which will relate to sort of our basic feedback topology of our input equals our error plus our feedback, as we can see by doing a KCL at our inverting input terminal. We're not going to investigate it, but we could also define an input resistance RIF as shown here, as well as an ROF, output resistance, which is not shown. So in order to do sort of a simplistic analysis of this circuit, what we're going to do is we're going to replace this amplifier here in the middle with a model of that. So something like this, where we have a dependent current source on the right. And so notice for a non-ideal model, we would have a resistance R out in here as well, but we don't have that. So we're neglecting our output resistance for that amplifier, R naught. Notice I've also dropped this RS resistance that was here. So before we had some source resistance, here we're going to ignore that as well. So as always, we're sort of making a lot of simplifications in order to get sort of an ideal or a first order approximation. One other thing that we're going to assume is we're going to assume that our error current is very small. So assume our I sub epsilon is very small, and so that sort of checks out with what we know about ideal op-amp analysis, because we know ideally we shouldn't have any current going into these input terminals of our op-amp. And another way to think about that is we know that we have sort of a zero differential voltage between our two input terminals in an ideal op-amp. So we're just sort of saying, keeping in line with that assumption, we're going to assume IE is very small, and we're going to say it's so small such that we can say that this voltage V1 is equal to 0. So we have essentially no voltage drop across this resistor Ri. Okay, so I think that's all of our sort of simplifications and assumptions out of the way. So now let's see if we can figure out our transfer function. So we're trying to look for our transfer function, and then we're going to compare it to our ideal form. Okay, so let's start by looking at our output current. So since we're neglecting that R naught, we don't have R naught for our op-amp model, we're saying our output current is just equal to that dependent source value, which is A sub I times our error current. And then coming back to our input side, we can see that our error current is equal to our input current, I sub I, which again, our I sub I is essentially the same as this I sub I prime up here above because we're neglecting RS, minus our feedback current I sub FB. Okay, so to be consistent with the notes, we can call this equation 1. And now what we can say too is we can sort of look at some voltages, and ultimately we're going to be looking for a way to get rid of this IFB term here. So we want this to just have I out and I naught. So we want to ultimately be able to substitute in for something there. So what we're going to start with is we're going to say our V out is equal to this VI over here on the left minus IFB times RF. So it's this voltage here minus the voltage drop here puts us at V out. Well, we know that our V1 is equal to 0 based on this assumption up here. So we can say this V out is really just negative IFB times RF. And so what we can do from here is we kind of see we have this IFB, so now we're trying to think how can we get that in terms of a V out, or sorry, an I out or an I in, so we can put it into this equation 1. So let's look now at our current I1, and once we know I1, we can relate that and our IF and IFB via KCL and substitute the result into our equation 1. So our I1, note on this resistor R1 we have V out defined as such. So from passive sign convention, if we're doing Ohm's law, that means we have I1 is equal to negative V naught over R1. So this is from our passive sign convention, which hopefully everybody remembers from ENG 301. So this then, we know our V out was defined up here. We can say this is equal to negative 1 over R1 times V out, which is negative IFB times RF. And of course we can rearrange that a little bit. We can say this is IFB, we have those two negative signs canceling out, and then a ratio of resistors, RF over R1. So now from KCL, if we're looking at KCL at this node here, we can see that I1 and IFB both go into the node, I naught comes out. We have zero current coming out this way because we don't have anything connected there. So we have I naught equals IFB plus I1. And so we just found that our I1 is equal to IFB. Let's try to write that so it's at least somewhat legible. Our IFB times RF divided by R1. So I've just taken the expression for our I1 from the previous line, substituted it in there. Of course, now we can factor out our IFB. So that's times 1 plus RF over R1. And of course, now we can solve for this IFB. This is equal to I naught divided by that quantity of 1 plus RF over R1. So what we want to do now is we want to substitute this IFB value into our IFB value up here in 1. And then because we're looking for our transfer function, ultimately we're going to be looking for our closed loop current gain, which is equal to our output current divided by our input current. Okay, so making that substitution then, what we're going to have is our output current is equal to A sub I times our input current, and then we substitute for our feedback current and we have I naught times 1 divided by 1 plus RF over R1. And now we can sort of separate our I naught terms, so let's put both of those on the left. So our I out is I out times 1 plus, now we have A sub I divided by 1 plus RF over R1 on the left, and then we're left with our input on the right, which is just A sub I times our input current. And so from here, it's pretty easy to find our closed loop gain, which is again equal to our output current divided by our input current. And we see that is equal to our A sub I in the numerator divided by 1 plus A sub I times the quantity of 1 over 1 plus RF over R1. And so if we compare this to our ideal form, we see it's actually the same as our ideal form, which hopefully is no surprise. Hopefully we saw that coming. And from sort of inspection, we can see that our beta sub I is going to equal to 1 over 1 plus RF over R1. So the same way that we saw with our op-amp example for our voltage amplifier, if we know our RF and our RF and our RI values, we know the beta value, And then we can go in there, and if we also know our gain value, A sub I, we can figure out our transfer function, we can figure out our input and output resistances with feedback, and so that can be a very useful thing to do when analyzing the circuit.